All right, so I want to take a look at graphing rational functions. A rational function is the quotient of two polynomials, right here, f of x equals p of x over q of x, where that denominator is not a constant, so that has to be a polynomial. It has to have some sort of variable. I will get graphs that look something like what I have right here. And we can expect that most rational functions are going to have at least two asymptotes. Generally, they will have two, one vertical and one horizontal. This also means that most of them are discontinuous. We talked about the idea of functions being continuous earlier in the year. To say they're continuous means that they can be drawn without picking up your pencil. Discontinuous would mean that there are two or more pieces of graph which are not connected, which is what I see right here. I have a curve down here and a separate curve up here to form this graph. How I figure out if something is discontinuous? Well, I'm going to look at domain restrictions. So if I'm trying to understand how to graph these, that's really the first thing I need to figure out. I need to look at domain, range, and asymptotes. So let's go ahead and dive into that. So first off, domain, vertical asymptotes, and holes. I see here a function f of x equals 2x squared minus 8x over x squared minus x minus 12. Now if I want to analyze this function, frequently what I will have to do is factor. So I'm going to factor both the numerator and the denominator here. And I can see that up top I have 2x times x minus 4. And in the denominator, x squared minus x minus 12 is x plus 3 times x minus 4. Okay, so I have to think about the domain. The domain will not include all real numbers. I know I have these things called restrictions. The denominator cannot equal 0. So the domain will be all real numbers except -3 and 4. And again, that's since the denominator cannot equal 0. Now what those things will do, how that's going to affect the graph is a different question. And if I look here, each of these factors is kind of telling me something different. I see this 2x up here. I see that there's an x minus 4 in both the numerator and the denominator. And then I see this x plus 3 in the denominator, which is giving me that restriction. Well, the big thing that I really need to know is asymptotes. So let's start off. The factor x plus 3 is only in the denominator. That is going to tell me about my vertical asymptote. This function will have one vertical asymptote, but it is entirely possible for a rational function to have multiple vertical asymptotes. This is really important. How do I figure out what that vertical asymptote is? Well, that factor x plus 3, I think about setting it equal to 0 and then solving, and what I get is x equals -3. So x equals -3 will be a vertical asymptote for this function. Now I also notice right here this factor x minus 4 is common to the numerator and the denominator. This is a bigger idea if you move on to pre-calculus. We will talk about it here, but it will not be heavily emphasized. This creates what is called a removable discontinuity, or more simply, a hole, which is to say that I'm going to graph this, and I would graph it like normal. I would draw a nice smooth curve looking something like what I have up here in the top left. But at a certain point, I would have a hole where I would draw just an open circle on the graph. So I would say here that there is a hole at x equals 4. Now, we're not going to emphasize this very heavily, so I'm not going to expect you to really know this, but I will tell you how you find the exact coordinates of the point at that hole. I'll go ahead and show that to you right here. So I see here y is equal to 2x over x plus 3 times x minus 4 over x minus 4. I've written it out like this to show you specifically. X minus 4 over x minus 4 is, for the most part, 1. X minus 4 over x minus 4 is 1, except when x equals 4. If I did substitute in 4 here, what would I get? Well, I would have y is equal to 8 over 7 times 0 over 0. Now, I know 0 over 0, that doesn't make any sense. But again, if I were able to divide this out, which for a lot of reasons we can't, what I would get is 8/7. So what I will find out is that I have a hole. My hole is at 4/8. Again, you're not going to have to know how to find that, but if you're watching, there it is. So we want to take a look at how to graph one of these functions. And I'm going to switch papers here because I was graphing this earlier and I kept making mistakes. So I want to make sure I do a good job when I graph this. So again, I want to figure out how to deal with this function. So I'm going to factor this again. This is 2x times x minus 4, and the denominator is x plus 3 times x minus 4. And we know that this is giving me asymptotes, holes, it's affecting my domain. It's also going to affect my range and give me a horizontal asymptote of some kind. Keep watching, we will talk about how to find the horizontal asymptotes. If you're trying to investigate a new function, I would urge you, of course, to always begin by looking at your calculator. And I have some stuff in there, that was something else I was doing. Now if I want to graph this, if you're graphing this on any calculator, what you would have to do is enter in 2x squared minus 8x, the whole numerator I put in parentheses, and I divide that by the whole denominator I put in parentheses. Okay? And then if I do this, I can go to the graph, and I can see that my curve should look something like this, my two curves, so what we call a hyperbola. But these two, this discontinuous function should have a graph that looks something like this. And if I want points, I can of course go to the table and find points. And I'm way down at 60 something, so I don't need to be there. I'm going to take set start 0 table. All right. And then I see these things right here. And I see a couple of errors. My errors are telling me about the restrictions. One of them, this is my vertical asymptote, x equals -3. The other one we discussed, x equals 4. So you can pull points off of here as you like to graph this. I have already made a sketch of this graph because, like I said, I was messing it up earlier and it was frustrating me. You see here I have a vertical asymptote, x equals 3. My horizontal asymptote, which I'll tell you about how to find in a minute, is y equals 2. And I've plotted some points to try and get a general idea of what this looks like. I've also tried to hug close to these asymptotes because that's what the function does. I have a few good points. Most of the points on these curves are not going to be very good, so really 2 or 3 points is probably going to be more than enough just to get the right idea of where it lies and how it behaves. You see I've plotted my hole. I did find the coordinates, but again, the idea is once I have this point right here, once I have this point right here, I have this point right here, I know I'm going to curve through this, and when I get to where x equals 4, I know I have a hole. So you see I've just inserted an open circle and moved on from there. Now when I'm figuring out domain, range, and all this other stuff, so my domain, there are two ways that you can write this, although one may be expected in certain contexts over another. The idea is the domain is all the real numbers with 2 values excluded. It's the real numbers with x not equaling -3 or 4. Now I can write it like that, but if I am asked for this in interval notation what I would write is, well, x can be really small and be everything up to -3. And then I have to skip over -3, go to the other side, things that are greater than -3 but less than 4. And then I skip over 4 and go to infinity. So that's how you would write that in interval notation. For the range, we can do something similar. The range is the set of real numbers such that y does not equal. When I look over here, I already figured out that my hole was 4/8/7. So that is the y value I'm losing down here. The other y value I'm losing, I see that this curve gets close to this asymptote, but the idea is it doesn't actually touch it. So my range would be y does not equal 8/7 or 2. And again, I could write this in interval notation in a similar fashion. -infinity, 8/7, 8/7, 2, and I've run into my own work here, 2 to infinity. For my x-intercepts, well, I've graphed it. My x-intercept right there, I can see this passes through the origin, so that is both my x-intercept and my y-intercept. One of the things, again, that we will talk about, if I look right up here and if I'm analyzing this, I can see that x minus 4, that's telling me I have a hole. X plus 3, that's telling me I have a vertical asymptote. Right here, this 2x ultimately is going to give me the x-intercept. And if I wanted to find a y-intercept, of course, you can always find a y-intercept by substituting 0 for x. My zeros, well, zeros and x-intercepts we know are the same thing. This means that x equals 0. And where is this increasing or decreasing? Well, what I see here is this graph is discontinuous. On this part of the curve, I am increasing, I'm constantly going up. And then at x equals -3, I don't have anything. And then I move to the next part of the curve. I'm increasing, I'm increasing, I'm increasing. I reach the hole, so for a moment the curve does not exist. And then I continue to increase. So what I see here is this is actually increasing over the entire domain. -infinity to -3, union -3 to 4, union 4 to infinity. For decreasing, it is decreasing nowhere. So I can write none. So that's a look at how we would analyze one of these. I apologize, this is a bit tricky because we're looking at how this works without quite understanding how to get all of this information. The next big thing that we have to look at is how do you find asymptotes? Pardon. We already found vertical asymptotes. What we need to look at are how to find horizontal asymptotes. Well, the idea of horizontal asymptotes is what you're going to do is compare the leading terms of the numerator and the denominator. Okay? And you have to think about a couple examples that I can show you right here. If I said something like y equals 15x squared minus 1 over 5x squared plus 9x or anything like that. Well, if I compare these leading terms, because I know as x approaches positive and negative infinity, these are going to weigh much more heavily than these other terms. If I look at those leading terms, 15x squared over 5x squared is essentially 3. So that's going to tell me about my horizontal asymptote. The horizontal asymptote deals with end behavior and really nothing else. One of the things we're going to talk about, or that comes up, is that rational functions can actually intersect their horizontal asymptote somewhere in the middle of the graph. The HA, the horizontal asymptote, is really telling me about end behavior. Both ends will approach the horizontal asymptote. Alright, so let's take a look. Here, I'm looking at the degree of the numerator and the degree of the denominator. So the first case is that the degree of the numerator and the denominator are the same. So I have equal degrees. In the event that I have equal degrees, what I want to do to find my horizontal asymptote is I say that y is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. So for example, over here, what I was just talking about, I see 4x squared over 2x squared. This is essentially the same as the example I just did a minute ago. If I'm looking at this, 4x squared over 2x squared is essentially 2. So my horizontal asymptote would be y equals 2. All right? What if they're not the same degree? Well, then I have two possibilities. Either the denominator has a higher degree, let's say the denominator is greater, or the numerator is of a greater degree. Well, if the denominator is greater, this is a little bit trickier. You have to think about something like this. Let's take a look over here at f of x equals 1 over x plus 2. If I look at the leading terms of both the numerator and the denominator, I'm looking at 1 over x. Well, here's the thing. As x approaches positive or negative infinity, 1 over x, you have to think about this. If I said 1 over 100, or 1 over 1,000, or 1 over 10,000, 1 over 150 billion, those are going to continually get smaller while still staying positive. So what happens is, as x approaches positive or negative infinity, 1 over x will approach 0. If the denominator has a greater degree, my horizontal asymptote is y equals 0. The last case, if the numerator is of a greater degree. Well, what's going to happen here is that I will have no horizontal asymptote. Think about it right here. X squared over x. Well, x squared over x is essentially x. Now, that is not a constant. X If x is very large, then x will approach positive infinity. If x gets very small, then x approaches negative infinity. So what this tells me is what the end behavior does. The end behavior follows closely to y equals this quotient, this x. So I won't have a horizontal asymptote, but I can actually say that, okay, the end behavior is following y equals x, which I know is a line that goes from low to high. So as x approaches negative infinity, this function would approach also negative infinity. As x approaches positive infinity, f of x would approach positive infinity. So I'm going to take a look at some examples right here just to work you through this. I'm going to work through these a little bit quicker because this video is already getting kind of long. 9x squared over 3x squared. Well, I see that the degrees are the same. If I compare these, I can just divide these and say 9x squared over 3x squared. Well, that's 3. So my horizontal asymptote is just y equals 3. And the idea is, again, as I said, horizontal asymptote tells you about end behavior. So both ends are going to approach any horizontal asymptote. Both ends approach the horizontal asymptote. So both ends will approach 3. All right. Take a look at another example. 12x minus 1 over 2x squared plus 5. Well, again, I look at the leading terms. 12x over 2x squared. I can think about if I simplified that, that would be 6 over x. And again, I think about as x approaches infinity, or negative infinity for that matter, as x approaches positive or negative infinity, 6 over x will approach what? Again, think about it. 6 over 100, 6 over 1,000. Sorry, I wrote the wrong thing there. That's going to approach 0. The numerator, the denominator is a greater degree. Which means the horizontal asymptote is y equals 0. So that means both ends will approach y equals 0. Take a look at one more right here. Example 3. H of x equals negative 2x to the 4th plus x minus 1 over x squared minus 16. Now again, mind you, I am only focusing on horizontal asymptotes. I'm not looking at how to find, or I'm not also looking at vertical asymptotes or holes or anything like that. I could find them here, but I'm focusing on horizontal asymptotes. So if I look at negative 2x to the 4th over x squared, if I simplify this, what I get is negative 2x squared. That's not a constant, and as x gets very large or very small, it will not approach a constant. As I put in 10,000, this will be negative 2 times 10,000 squared, which is negative 2 times a very large number. So what happens? There is a higher degree in the numerator, which means there is no horizontal asymptote. But what can I say? Horizontal asymptote, there isn't one. My end behavior follows y equals negative 2x squared, which means both ends will go down. If you think about this, this is a parabola with a reflection in the x-axis. So both ends will approach negative infinity. Now I've done some examples here. There are always more examples, and in particular something you need to be aware of. There is a nicer transformational form of rational functions. A over x minus h plus k, or for that matter, I could say x minus h squared is another real common form of this. But in this form, since a over x minus h, that itself would tend towards 0 for large x's. This has a horizontal asymptote of y equals k. All right? So when I see it in this different form, I need to know that as well. All right, let's do a few examples. Here, I want to determine domain, asymptotes, holes, and behavior for each rational function. So on the first one, this is in that transformational form I was just talking about. I look at my restrictions. Clearly, x cannot equal 3. It's x minus 3 squared that will affect the graph, but in terms of the domain, I still have only one restriction. So my domain, I can say that x is not negative 3. I'll write this in interval notation. Excuse me, x is not positive 3. So my domain is everything but 3. Vertical asymptotes and holes. I have to answer these questions simultaneously, really. Well, there are no common factors to the numerator and the denominator. The numerator is just a constant. So there cannot be a hole here. Okay? No common factors to the numerator and denominator. No common factors to numerator and denominator. Which means x equals 3 will actually just be a vertical asymptote. And again, for the most part, holes, not trying to be confusing, but they are a little bit less important in Algebra 2 because we're focused on a bit more of a basic level. If I want the horizontal asymptote, again, in this form, I know to look here. Y equals 6. So for my end behavior, as x approaches negative infinity or positive infinity, both ends will tend towards that horizontal asymptote of 6. All right, if I look at number 2, well, this is not factored, and that's really what I want to do. If I factor the numerator, I take out a negative 3, get x squared minus 25. I factor the denominator, that is x plus 8, x minus 5. I can factor the numerator a little bit more, and then, aha, I see x minus 5 is a common factor to the numerator and the denominator, which means I will have a hole at x equals 5. And again, if I wanted to figure out the coordinates, if I needed to, I could do that, but let's just leave it at there's a hole at x equals 5. My domain will be all the real numbers except for negative 8 and positive 5. I will focus on writing this in interval notation. Everything but negative 8 and 5, so I skip over those. Vertical asymptote. Well, x equals 5 is a whole. The vertical asymptote is x equals negative 8. For the horizontal asymptote, I know I want to compare the leading terms. I compare negative 3x squared and x squared and say, hey, that's basically negative 3. So my horizontal asymptote is y equals negative 3. As x approaches negative infinity, this should say y, not f of x, so forgive me on that. Y. Both ends will approach the horizontal asymptote of negative 3. A couple more examples, a couple more things to say, trying to wrap this up. 4x minus 1 over x squared plus 10x plus 21. So if I factor that denominator, up top I still have 4x minus 1, that's not factor. What multiplies to 21 and adds to 10? Well, that would be positive 3 and positive 7. So x plus 3 and x plus 7. So my domain, again, I'll write it in the short way, just for a variety. The real numbers with x not equaling negative 7 or negative 3. What vertical asymptotes and holes do I have? Again, there are no common factors, so I do not have a hole, but I have 2 vertical asymptotes here. X equals negative 7 and x equals negative 3. So that will create an interesting graph if you want to take a look at this yourself. And I will have a horizontal asymptote. What will it be? Well, for the horizontal asymptote, I compare 4x and x squared, which is essentially 4 over x. And as x gets very large, 4 over x will get closer and closer to 0. And this should say g, not f. All right. Let's take a look at number 4 right here. 6x squared plus 5x minus 4 over 4x. I could try and factor the numerator, negative 24 plus 5. That sounds doable. That's 8 minus 3, right? So if I did this, I would have 2x, 3x, plus 4, minus 1. But in order to answer these questions, I really don't need to factor that numerator because it's not going to tell me anything. I could really judge based on this original equation that x was not a common factor of the numerator and the denominator. No common factors means no holes. My domain, again, is all the real numbers except for 0, or in interval notation, negative infinity to 0, union with 0 to infinity. My vertical asymptote is x equals 0. My horizontal asymptote there won't be one. Why? Well, 6x squared over 4x is 3x over 2. That does not tend towards a constant for large x's. So 3x over 2 is where I have to leave that. That tells me about the end behavior, though. For end behavior, think y equals 3x over 2, or 3 halves x. It's a line with a positive slope. So as x approaches negative infinity, h of x should approach negative infinity as well. And as x approaches positive infinity, h of x will also approach positive infinity. Okay, so hopefully that makes sense. Again, finding the asymptotes, that's a really important part of what we're doing with graphing rational functions. And certainly that's something that I would hope and expect you to know how to do without a calculator. Some other things to note before I go ahead and stop. The range of a rational function can be difficult to figure out, especially for rational functions with multiple vertical asymptotes. Don't be afraid to use your calculator. Of course, a calculator is a good tool, and we should use it strategically. These can look very strange, so this is a good time to check to make sure it looks the way you're expecting it will. Although we will primarily focus on rational functions of two types. But if you look, you'll find out that there are rational functions that look something like this, which would then have a range of all real numbers. Or I could have something very strange where, again, if I throw in two asymptotes, I could have something that looks more like this. And this could possibly, come all the way down towards the asymptote, or more likely it would stop at some value up here. So you just don't know. These can be very tricky. Although, again, we're going to limit what we look at a little bit. Another point. I made reference earlier to the fact that most rational functions are discontinuous. They do not, however, have to be discontinuous. In this example right here, I know in order to figure out whether or not it's continuous, I want to consider the domain, which means I would try and factor this. X squared plus 36 is a sum of squares. A sum of squares does not factor. And what's more, if you recall, you know that it only has non-real solutions. If I set this equal to 0 and solved, x squared plus 36 equals 0 gives me x squared equals negative 36. Gives me x is the positive or negative square root of negative 36, which is not real. Okay, so the domain is all of R, since x squared plus 36 has no real zeros. So that's some food for thought. Okay, if you have a denominator that has no real zeros, then your rational function will still be continuous. Another big thing to think about is finding intercepts. Y-intercepts can be found as usual. X-intercepts take a little bit more work. Remember, Y-intercepts means X is 0. X-intercepts means Y is 0. So if I wanted to find, for example, the Y-intercept right here, I would put in 0 for X, and I can determine pretty easily that the Y-intercept would be negative 2/6, which is negative 1/3, minus 5. So that's negative 5 1/3, or negative 16/3. But if I want to determine the x-intercept, I have to work a little bit harder. I have to make y 0. So I would say 0 is equal to negative 2 over x plus 6 minus 5. And then I can solve this. I can add 5 to both sides. I can multiply by 6. And then if you distribute and solve, I'll leave this to you, but if you distribute and solve, what you're going to find out is that the x-intercept is at 32/5, 0. Also important to note, here, if you look at the difference between f and g, F is that transformational form we made reference to. G is more just a simple quotient of two polynomials. Well, if I wanted to figure out its y-intercept right here, the y-intercept is 0, 3. I'll leave that to you. Well, it's just negative 48 divided by negative 16. If I wanted to figure out the x-intercept, well, I would have to think about x squared minus 2x minus 48. That's x minus 8 times x plus 6 over x squared minus 16. Well, if I want to solve this equation where that equals 0, the only way a fraction can be 0 is if its numerator is 0. So x minus 8 equals 0, x equals 8, x plus 6 equals 0, x equals negative 6. You should go and check for restrictions. X squared minus 16 factors as x plus 4, x minus 4, so x should not equal 4 or negative 4. I can get either one of those. So I would see that I have two x-intercepts for this problem, 8, 0, and negative 6, 0. Again, I know it's a lot of information at once. That's why I'm making this video, so you can look back through it, see what questions you have, maybe ask some more focused questions in class. Thanks for watching.